Welcome back. Now from that short break, now let's look at impact. Okay. So remember, when bodies collide, impact is created, right? So this occurs for a very short time, right, or a very short period of time, causing relatively large impulsive forces between these colliding bodies. So now there are types of impact, right? So we have types of impact. First is a central impact, right? We're going to also look at the angular impact, okay? First, let's look at the central impact. So how does central impact occur? So occurs when the direction of motion of the mass centers. Now listen, we're looking at bodies, okay? One body, another body. So we have the mass centers, okay? So now, central occurs when the direction of motion of the mass centers of the two colliding bodies is going this direction, right? And this is colliding in this direction. So occurs when the direction of the direction of motion of the mass centers of the two colliding particles is along a line passing through the mass centers. So that means that if this is the center and this is the center, so there should be a line through the center. My pen is not straight, but let's assume this is passing through the center right here. Okay, let's assume this is the center. Let's assume this is the center. So if that's what we have, and this line has to be perpendicular to the plane of contact, right? So now, if we have this is VA, right? This is particle A right there. And also we have VB, it's velocity, VB, okay? Because it's a condition that we need. So if we have this and this is what now they are colliding, then this central impact occurs when these two collide, but they are in line with the central line that passes through the centers of these particles, okay? So let's see, continue to drive into this and see what I'm trying to explain. So now, this is how these particles are occurring, right? We have particle A, particle B, but they collide, and this collision goes through the line of impact, which is the line that passes through the center of mass of these particles, okay? But now you see, this is perpendicular to the plane of contact. This is our plane of contact, right? So now, we also have oblique, or we should maybe call it maybe angular impact. So this one occurs, right? It occurs when one or both particles make an angle with the line of action. Now, this is the line of action, right? This is the line of impact, right? And then this is a plane of contact for which these bodies are in contact after collision. And then one of the bodies is moving, or another at an angle. Let's call that angle. Let's say A is making an angle which is oblique, which is theta. And then the other one is making an angle which is oblique, which is phi, right? So what this kind of impact is what we call oblique impact. Okay. So now, illustration of the method of analysis of mechanics of impact. How do we go ahead with solving problems with impact? First of all, this is what's going to guide us. First of all, collision will eventually occur, right? Collision will eventually occur provided that the velocity of the first particle, right, is greater than the velocity of the second particle, okay? Like we seen previously in the previous example, there was collision, right? But later on in the other example, these two move together afterwards, okay? Now, that is the first thing for us to take note, that collision will eventually occur if the velocity of the first particle is greater than the velocity of the second particle. Again, during collision, the particles are deformable, right? Or non-rigid. He said that they exert an equal but opposite deformation impulse, right? Meaning that now if our force is P times the change in time of that's what we call the impulse deformation. That is which each of them is exerting onto the other. So this is the deformation impulse, right? Which we can get by the force of impact times the change in time, right? Again, only at that instant of maximum deformation will the particles move with common velocity. So now once at that instant, then the particles are moving, they're going to unite, and then they're going to move with a common velocity v, since relative motion between them is zero. Because when they collide, relative motion is zero, so that means they're moving with common velocity. So at that instance, we have to mark those three important points during analysis. Okay. Let's continue more to learn this. Okay. Another one is that after a period, afterward, a period of restitution, right, occurs in which these particles return to their original shapes or they remain permanently deformed. Okay, so now also the equal but opposite restitution impulse, which now we are going to look at this restitution impulse, which occurs after the reaction, which we have another force of reaction or restitution, the restitution force, and then times the time, right? The time change, which now pushes these particles apart from one another. In reality, this force, that force of impulse, right? Or the impulse, this force that causes impulse, or the summation of these impulses, right? After collision, right? Should always be greater than the restitution impulse. Okay, should always be greater than the restitution impulse. So another thing to note is that just after restitution or these big things separating, okay, will the particles have the final momentum? Okay, they'll have a final momentum whereby now the momentum of the second particle, also the velocity of the second particle should be greater than, okay, the momentum of the first particle, right? Because when they collide, this one pushes it more, and then the other gains more energy or gains more velocity, and then it will now show that this one has lost velocity because of collision, whereas the second particle has gained more, right? So even in a simple faculty of common sense, we can see that that really happens, right? Anyhow, let's dive into this more and get this going. So this is just a simple illustration of the of restitution impulse, right? So now this is when the particles are together, that is A and B, right? And then we have effect of A on B and also effect of B on A. That's now we have the restitution impulse, and then afterwards these two separate with VA2. That's the velocity of particle A after collision and the velocity of particle B after collision. But you realize that the velocity of particle B will always be greater than the velocity of particle A. So that's what we are trying to explain. So in most problems, VA, or the velocity or the initial velocity of particle A and the initial velocity of particle B are always known, right? Or they always tell you the particle is moving with velocity, the particle B is moving also with this velocity, and we only need to find the final velocity of particle A and the final velocity of particle B. So in this regard, the initial impulse of deformation and restitution cancel out, right? Because they're equal, right? You see, in most cases. And then when they're equal, that means that we are going to go back to the principle of conservation of momentum. right? And okay, that's what we're trying to say. Therefore, we are going to go back to the principle of conservation of momentum, which means that momentum of particle A plus momentum of particle B should then be equal to momentum after collision, which is the momentum of particle A plus momentum of particle B after collision. That means momentum before collision should equal to momentum after collision, right? I remember those things, you guys still recall. Okay, now applying the principle of impulse and momentum to each particle alone for both the deformation and restriction phases, right? We can we can carry out that. So now, applying the principle to particle A, then during deformation, if we just consider each particle, then we shall now see that during deformation, right? During deformation, collision, we know that now the particle initially moves with velocity v1. So meaning that the mass, its momentum, initial momentum, right, minus the deformation impulse should equal to the mass, should equal to the velocity, right? Should give us the momentum, right? To give us the momentum, right? Of which we have a common velocity right here. Again, during restitution, right? During restitution, so we shall have the common velocity right here, which we got, minus, this will be plus because the restriction is in the opposite direction. So now, because after impulse, the particle will move with the common velocity, but after moving with the common velocity, these particles will separate. As they separate, they're causing what we call restriction, right? So because it will be negative, that's why we're having a negative sign right here. So now we shall have the impulse due to restriction, and then this will now equal to this will be equal to the final momentum of that particle, right? So where V is the final velocity, right, of the deformation, and it's the initial velocity for restitution. So this is this is the final velocity for deformation, whereas when we start deformation, it becomes the initial the initial velocity for restitution. So that's why when we try to we put this together, this one cancels, and then the deformation and the restitution also cancel out, and then we end up getting that we conserve the principle of momentum. Right, anyway. So now, I need to find the coefficient of restitution. How do we find the coefficient of restitution? Okay, so we need to know how do we find the coefficient of restitution. Okay, so now let's learn how to find the coefficient of restitution. The coefficient of restitution is going to be the ratio. Okay, it's the ratio between restitution impulse to deformation impulse. Okay, so from all these equations, we can find restitution impulse, we can find also deformation impulse. So deformation impulse is that means that it is the integral of the restitution force times the change in time. Whereas also deformation right here would be given by the deformation force and times the change in time. So we are trying to integrate to sum up the total deformation impulse. Perfect. I hope that is clear for each and every person. So now, for a body A, the coefficient of restitution is given by, will be given by the integral of r dt over p dt. So now, when you see, we had a common velocity, which is the velocity after deformation, as well as the velocity, the initial velocity before restitution. Okay, so that was the V. So our V, when we arrange the equations, let me go back. When you do rearrange these equations right here, when you do rearrange, you realize that we are interested in getting this product, this part here. So you realize that the M will cancel, and then we shall get MA over V, and then we shall get this one minus that over PDT, right? And then also we shall also get this one here. We make this the subject. We shall get integral RDT as MAV minus MAVA2, right? And then we get now the ratio, and the m's will cancel, and then our final equation, right? Our final equation now would be given by this equation, right? We shall have V minus V8 over VA, or the final velocity of that particle, over the initial velocity minus the common velocity. So the same with B, it will be with just the same thing, which is going for now. For B, you remember, for B, we will also write out these equations for B, but now here they're different because B has the final velocity being greater than that of A, right? So that means that we shall now, if we write out the equations, we shall end up having VB, the final velocity, minus the common velocity over the common velocity minus the initial velocity. Please, you can make sure that you know how we come up with this. I've not written down the equation for particle B, but in your free time and also in your discussion groups, you can try out that, because this is just very easy, right? So we've now to come up with coefficient of restitution. So let's proceed. Okay. So we've finished our coefficient of restitution. So let's also try to find V, right? Eliminating V, so we obtain. If we try to eliminate V from this equation right here, so we are going to obtain that VB minus VA over VA minus V. The final velocity of particle B minus the final velocity of particle A over the initial velocity of particle A minus the initial velocity of particle B, right? So if E is known, right? If we know E, if we know the coefficient of restitution, then we can find the final velocity of particle A, as well as anyway, if E is known, the final velocity of particle 2 and the final velocity of particle A, okay, the first particle and second particle can be calculated, right, from this. So note, remember to establish a sign convention for defining directions. So you have to know that which one is positive, right? Which one is negative. For example, if this particle is going this side, you may choose this one to be positive. Whereas if this particle is going this side, you may choose that to be negative, okay? So you need to know the sign convention. All right. So coefficient of restitution E is relative velocity just after impact over relative velocity just before impact. Remember, relative velocity after impact is the same as velocity of the second particle minus velocity of the first particle. Whereas relative velocity just before impact is the velocity of the first particle minus velocity of the second particle, and has values between 0 and 1 because it is a ratio. Also, elastic impact. Now, we need to know what is elastic impact. Elastic impact occurs if the coefficient of restitution is equal to 1. This occurs when the deformation impulse is equal to the restitution impulse. So that means that the integral of PDT is the same as the integral of RDT. Also, we have what we call plastic impact. Plastic impact occurs when the ratio is 0. That means that A restitution, coefficient of restitution will be equal to 0. And in elastic impact or plastic impact occurs when E is 0. So that means that no restitution or impulse for inelastic elastic collision, and the particles, and in this case the particles stick together or they couple, right? Couple means they move with a common velocity. So now, note, from observation, the principle of work and energy cannot be used for analysis of impact, since we do not know the internal force variation on deformation. So therefore, we cannot bring in the principle of work and energy in these particles, right? Or in the study of impulse and collision. So now, deformation and restitution, or how they display during collision. But anyway, after knowing these velocities, after knowing the velocities, the second velocity, that means the velocity after restitution and for both particles, so then the energy loss during collision can be calculated. Okay, we can calculate the energy loss because now we can find work done before collision and after collision, right? Because we know the velocity. Now, okay. All right, they're saying that after knowing these velocities, then the energy loss during collision can be calculated. Perfectly elastic impact, no energy loss, right? And for plastic energy is lost is maximum, right? Anyhow, we are going to see all that. So now, let's see an example. The bag A, there's a bag right here. The bag A right here, okay? Having a weight of 6 pounds is released, right, from rest at the position where theta, this angle right here is 0 degrees, okay? Now, after falling to theta, which is 90 degrees, it strikes, okay? It strikes this box right here, which is our box B, right? If the coefficient of restitution between the bag and the box is 0.5, that means E is equal to 0.5. But remember, E is the ratio of relative velocity after restitution of relative velocity before deformation, right? So, okay. So now, determine the velocities of the bag and the box just after impact. What is the loss of energy during collision? These are very good numbers to set for exams, right? And also for tests. Okay, so now we know this, we know the angles, right? What else do we need? We know the weight, which is this. So now, what else do we need? So now, let's try to learn how to solve this equation, or sorry, this question. First of all, this problem involves what we call central impact. Okay, why? So before analyzing the mechanics of the impact, it first necessary for us to obtain the velocity of the bag just before it strikes the box. Okay, so we need to find the velocity of this bag. With a bag? This bag right here before it strikes the box, right? Because the box is right down here at position 1. So now, remember conservation, the principle of conservation of energy. So we need to find our datum, right? We need to find our datum. So our datum is right here, and they had given us the height, right? They had given us the height, okay? Because it was 3 feet, right? So when we go back, realize that our height here is 3 feet, okay? So now we also have the weight, okay? And now at that point, and as well at point 0, as well as at point 1, okay? So now, remember, we have our datum and we have different angles. At point 0, the angle theta is 0. At point 1, the angle theta is 90 degrees, right? So now let's start with position at theta, at the datum. At theta is equal to 0, right? At theta is equal to 0. The conservation of energy, we know that we have T naught, right? Plus V naught is equal to T1 over plus V1, right? So initially, remember our T naught is the kinetic energy, right? So we're now conserving energy. So we're saying that kinetic energy before collision, before at the datum, plus the potential energy, which is V naught, is the same as the kinetic energy plus at 1 plus, okay, the kinetic energy at point 0 plus the potential energy at that point is equal to the potential energy at point 1 plus the, this is kinetic energy and this is potential energy. So now that's what we are trying to conserve energy, because we are interested in finding the velocity. And we know that we can only find velocity if we relate the energy, the principle of energy. Energy can never be created, but it transforms from one form to another. So now we know that this particle moves from one datum, which is a point zero, when the kinetic energy is zero, and then the potential energy is maximum. And then moves from there, hits point one. At what point one, we know that the potential, it has both kinetic energy as well as the potential energy. But at that point one, the kinetic energy, so the kinetic energy is maximum, whereas the potential energy is zero. So now that's what the principle we are going to use, right? So now at that point, so this is what we are going to feed in. Right. So at this point, at the datum, we don't have potential energy, we don't have kinetic energy, we also don't have potential energy, right? But at this point, we are going to have kinetic energy, whereby T is given by a half mv squared, right? A half mv squared, right? But the potential energy is negative, right? We're going to say that the potential energy is negative. So now we are going to, that's why we have here our mass. Remember, we need to, at least we need to know the acceleration due to gravity, because now this is not in kilograms, so it is in pounds. For pounds, the acceleration due to gravity is 32.2, right? That is feet per second squared, okay, which is right here. So that means this is our acceleration due to gravity. So now now we are trying to get the mass, because we have 6 pounds divided by 32.2 feet per second, but we don't know the velocity of that particle at this point. But remember, also we know that our V1 at that point, that is potential energy, is given by mgh, okay? Whereby now mgh is the pound, which is the 6 pound. Now we times h, which is the 3 feet. So that's why we have this, but it is negative because work done against this is in the opposite direction. So now from there, we equate these two equations, we are able to find our velocity at point one being equal to 13.9 feet per second. Okay, so now we've known the velocity of that particle. All right. Now, since we know the velocity of that particle, we also know the first velocity, the v naught, we know it, so it's 0. So now we know v1a, we know that, and then we are going now to start bringing in conservation of momentum. So we first of all did with conservation of energy. So now let's now continue bringing conservation of momentum. So now, after impact, we will assume that A is the what? Is a bag, and B is the box. Okay. So after impact, we assume that A and B travel to the left. Okay. That means that once the what? Once our bag hits the box, it will move to the left, right? That means that the box will have more force. So I mean, we'll move a bigger velocity, pushing this thing to move to the left, right? So that's what we're trying to say. So applying the conservation of momentum to the system, so we know that moment before collision is the same as moment after collision. So that means that moment of the bag, that means that we are using now velocity. So now of the bag before collision, that means at point one, at this point one here, right? Before it hits the box. So we are going to have the moment of the bag, right, let's say the moment of the box, sorry, the mass of the box times its initial velocity, right? Because the box was at rest, so that means the velocity here is 0, okay? Plus the mass, sorry about that. Let's continue. All right, let's continue. All right, so we were still looking at We're still looking at this. So we said the mass of the box. Now we're looking at the momentum here, and we say this velocity here is 0 for the box. Now, how about the bag? The bag has a mass, which we know it is 6 divided by 32.2, and its initial velocity, which initial velocity we got it as VA1, right, is the same as now, which we are saying that they all move to the left. So that means they move with this common velocity. Sorry, they move in the same direction. That means that there's no minus. All of them are moving in the left. So that means that we shall have the mass of the box times the velocity, the second velocity, plus the mass times the mass or the momentum after collision of particle A, which is our bag. So now when we try to feed in, we realize that this component is 0, whereas this component, we have this, and then we can multiply with the mass, which is 6 divided by 32.2 times the acceleration, which we had got, which is 13.9 right here. So it's what we are multiplying, is the same as, now remember the box has its weight, which was 18 divided by 32.2 to get the mass times final velocity, which we don't know, right? Plus the mass of our bag, which we know, times its final velocity, which we don't know, right? From there, we can now get our equation, right? From there, we can get a relationship between VA, or the final velocity of the box, and the final velocity of our bag. So this is for the box and this is for the bag. And then we realize that our VA is the same as 13.9 minus 3 VB, or the final velocity of the box. But remember also our E is the same as, they gave us the value of E, which was 0.5, remember? And then we remember that E is the same as the velocity of the box, okay, which is VB 2, right, minus VA 2, right, over the initial velocity of VA, which we have as 13.9, minus the initial velocity of the box, which was 0. So now, but we know this also. Now we're going to get that equation, and then we are going to solve. Perfect. So now, that is very easy. So this is now a dry coefficient of restriction, realizing that the separation occurs. So this is what now I've been explaining. This is what I just written up there. And then we are going to relate. And this is 0.5. We know n of this. Then this is this, what I've just seen. It's done. And then we have our VA2 right here. We have two equations. We can solve them simultaneously. And then we are going to realize that our VA is going to be 1.74 feet per second, and our VB is going to be 5.21 feet per second. Now, the next thing that we need to know is, how do we determine the energy loss? How do we determine the energy loss? How do we get the energy loss? That is very important, okay? Now, for you to get the energy loss, we are going to apply the principle of work and energy to the bag and box just before collision and just after collision. So now, remember, we say that, remember from our energy principle, we say that the summation of energy, right? Okay, let me get it again. Remember, we say that T1, right, plus the summation of energy, right, from one point to another, okay, is the same as the final kinetic energy of that particle. So the initial kinetic energy of the particle plus the work done by that particle is equal to the total kinetic energy gained by that particle. So that's what we are trying to put. So it is now, you just make the energy, the work done, the subject. So this one crosses to that side, and that explains what we have right here. Right. So now, that means that the kinetic energy of the second particle minus, the kinetic energy after collision minus the kinetic energy after collision. So now we have this. So for the box, now we are going to have the velocity that we've got for the box right here, and also for that of and that of the bag, right? So now we are going to get that energy. So now this is kinetic energy. Remember, T1 is kinetic energy, which we know is given by a half mv squared. Okay, a half mv squared. Okay, that is our T1 or our T, and then for this particle to be a half, right? All right. All right. Sorry for that. Let's continue. We're talking about energy loss, and we were getting the kinetic energy. So now we're getting the kinetic energy for the box right here, plus the kinetic energy for the bag. Okay. Minus. Okay. Minus. That is now that is our T2. Okay. Minus, now we are going to get the T1, which is the initial kinetic energy. Remember, the box did not have any velocity. That means that its T1 is 0. Remember? So we're not going to include it, but we're only going to include for the box. So that's why we have a half here, 6 over 32.2 times its initial velocity, which is initial velocity over 13.9. But remember, this is a half mv squared, so that will be squared. And there you realize that the energy that we are getting as the energy loss is a negative energy. That will be energy given by feet times or the pounds times the feet, right? Because those are the units. These ones will cancel out, and then we have this. So we shall have all. So we shall have 10.1 feet times a pound, right? So if you try to compute all this, you come up to this. I hope that is very much explained. What we did is we got the sum. We did not want to do it for individual. We just summed it up for both particles. This is the initial, the final kinetic energy for both particles minus the initial kinetic energy for both particles. So that's what we've done, and I hope that is very clear for all of us to understand. Now, having gotten that example, there are more examples for us because